Hey, welcome. Sometimes the biggest ideas in science are hiding inside the simplest questions. Today, we're going to tackle a classic physics puzzle about a floating box, and in the process, we'll uncover the secret of how massive ships conquer the oceans. So let's dive right in. So let's start with a simple discovery. Picture this. You're out on a lake, it's a calm day, and you spot something kind of strange floating in the water up ahead. And there it is, a big, mysterious box just bobbing there. Now, you're curious, and you start to wonder. The key question here isn't, what's inside, but something much more fundamental. How much water is this thing actually pushing aside to stay afloat? To solve this, we don't need a ton of information. We just need two key facts. First, we're in a freshwater lake, and trust me, that detail is more important than you might think. And second, after you pull the box out of the water, you find out it weighs exactly 75 kilograms. That's it. That's all the info we need. Now, to find our answer, we don't need a supercomputer or some complex modern lab. Nope. We just need to take a little trip back in time, over 2,000 years, to a brilliant insight from ancient Greece. And here is the big idea, Archimedes' principle. It's so elegant and powerful. All it says is that for anything to float, it has to push aside an amount of fluid that weighs the exact same as the object itself. It's a perfect, beautiful balance. You know the story, right? Legend says Archimedes figured this out while getting into his bathtub and seeing the water rise. He was so blown away by this sudden insight that he famously shouted, "Eureka!" which means "I have found it," and, well, ran through the streets. It's just a great reminder that a simple observation can totally change our understanding of the world. Okay, so we have the principle, but how do we get from the weight of the water to the volume of the water, which is what the question actually asks for? Well, let's connect those dots. Just think of it like a physics tug of war. You've got gravity pulling the box down with a force that's equal to its weight, but at the same time, the water is pushing up. That upward push is called the buoyant force. And for that box to float peacefully, those two forces have to be perfectly, exactly balanced. And here it is. This is the key that unlocks the whole puzzle. Remember how I said that being in a freshwater lake was a big deal? This is why. For freshwater, the relationship between weight and volume is just incredibly simple. 1 kilogram of water takes up exactly 1 liter of space. That simple one-to-one conversion is basically our magic wand here. All right, we have everything we need. We've got the principle, we've got the facts, and we have our secret conversion key. It is time to put it all together and solve this thing. We're just going to follow a really clear 4-step process. First, we start with what we know, the weight of our box. Second, we bring in Archimedes' simple rule. Third, that rule tells us the weight of the water it's got to displace. And then finally, we do that super simple conversion from weight to volume. Okay, let's just do it. We know the box weighs 75 kilograms. So, according to Archimedes, to stay afloat, it must displace an amount of water that also weighs, yep, you got it, 75 kilograms. The weights have to be identical. And just like that, by connecting a few really simple ideas, we have pretty much arrived at our solution. The number is 75. But 75 what? That's where our freshwater connection comes right back into play. Since we know that 75 kilograms of freshwater has a volume of exactly 75 liters, well, there's our answer. The box displaces 75 liters of water. Simple, elegant, and really, really powerful. So why does a little puzzle about a floating box even matter? Because this exact principle is what allows a 100,000-ton aircraft carrier made of solid steel to float. Its hull is shaped just right to displace an enormous weight of water, which creates a buoyant force strong enough to hold the whole thing up. It's totally fundamental to designing anything that goes in the water. And that brings us to one last thought to chew on. We solved this for a freshwater lake, but what would happen if our box was floating in the ocean? Now, salt water is denser than freshwater, so would the box need to displace more volume or less to support that same 75 kilogram weight? Something to think about. Thanks for joining me.